Hello, everyone. Welcome to another SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Joining me today is Daniella Dellagiustina from the University of Arizona's Lunar and Planetary Laboratory. So welcome, Danny. Thank you for joining us.
Yeah. Hi, Beth.
Good to see you again. Thank you everyone for joining us to watch as well. Welcome to our viewers from around the world. Please let us know where you are watching from. What we're talking about today, NASA has extended the OSIRIS REx mission, which recently took a sample of the asteroid Bennu, and they've given that mission a new name and a new target. Now called Osiris-APEX or Osiris-Apophis Explorer, the spacecraft is going to swing by and study the infamous asteroid Apophis. This asteroid was discovered in 2004, and calculations performed at that time had it hitting Earth in 2029. However, more recent calculations based on many more observations have saved us from that fate. So now scientists have a chance to get up close and personal with the once deadly asteroid. So thank you again, Danny. I am really excited about this new mission, and I'm sure a lot of people are as well. But I'm also sure that the person most excited is probably you.
Yeah, I'm pretty stoked.
So let's start with talking about OSIRIS REx so we can kind of catch everybody up who might not be aware. OSIRIS REx went to Bennu, and then you guys did a wild sample of it. How did all of this take place? What was the process that it went through? What did they sample? What's going on so far?
Okay, so the OSIRIS REx spacecraft sampled asteroid Bennu in October of 2020, and it was a really it was a difficult road to get to that milestone. When we arrived at Bennu in 2018, the surface was just way rockier and more rugged than we had predicted based on all of the data we had taken of Bennu from the ground, from ground-based telescopes and the Spitzer Space Telescope, which was operating at the time. And so we really had to rearrange our plans and develop a new strategy for selecting a sample site. And we had to do that quickly because our opportunity to leave Bennu was in May of 2021. And that was a kind of a hard stop in order to make it back to Earth and do the sample return part of the mission. But we figured it out, and we ended up doing our sampling in 2020 in the middle of the pandemic remotely. So, another hurdle for our team that we had to overcome. But we think we collected more than the 60 grams of sample. That's our minimum requirement. And we think this is of a relatively pristine part of asteroid Bennu. It was from a small crater in the north that looked like maybe it had been recently excavated, and did have some signatures of organic material. So we are really, really excited for the sample, and the sample will get returned to Earth in September of 2023. So about a year from now. It's getting really close. And that will kick off this period of sample analysis for 2 years. And so we have a huge segment of our team that will be studying the sample. And right after the sample return, we're also going to put the spacecraft into a new trajectory that is going to allow us to rendezvous with asteroid Apophis in 2029. So next year is going to be an incredible year for me and the team, and it's going to be the start of 2 new parts of the OSIRIS REx mission.
So you said that you have a 2-year sample analysis period in between the 2 missions, but I have noticed a wealth of papers already coming out about Bennu and what we've learned from it so far. So what are some of the key takeaways that we already know about this asteroid that we learned during this mission?
Yeah, that is a great question. So we learned a lot by studying Bennu with OSIRIS REx. Bennu is really hydrated, so it has a signature in the light that's reflected from its surface that indicates that it is full of water-bearing minerals. And that's really exciting because we know that the meteorites on Earth that have really similar properties to asteroid Bennu. Their water is similar in composition to Earth's water. So we think that Bennu may look like some of the objects that delivered water to the early Earth. And that's really cool. We're going to learn a lot more about that when we bring the sample home. But we have these early indications that it's very hydrated and could be a good match for Earth's water. We also learned a lot about how much mixing takes place on small, what we call rubble pile asteroids like Bennu. And so these rubble piles are basically the reaccumulated rubble of an ancient collision that took place between Bennu's parent body and some other object. And we have had pretty limited data on these rubble pile asteroids to date, as far as understanding them as worlds and not just point sources of light. But between the 3 different data points that we have, which would be asteroid Bennu and then Ryugu and Itokawa, which were studied by the Hayabusa 2 and Hayabusa missions respectively, we think that these rubble piles might sort of represent collections of a number of different collisions that took place on their parent body and maybe other precursors. So an odd thing we found on Bennu were giant boulders that have the exact same composition as asteroid Vesta. And for those of you who might remember, Vesta is one of the largest asteroids in the asteroid belt, and it was visited by the Dawn mission a couple years ago. And so for us to have samples of Vesta on Bennu, it really indicates the level of mixing that took place in the main belt. And it was a pretty unexpected finding. Finally, just about a week ago, we released the results of the interaction of our sampling mechanism with the spacecraft, on the spacecraft with asteroid Bennu. And those results were interesting because 1, we collected the sample, but 2, because it showed us that the surface of Bennu is exceptionally weak. It might have properties more similar to snow than rock, which is kind of bizarre to think about. And you don't learn that unless you directly go up to an asteroid and you poke it. And so we were really excited to have those results released to the whole world through 2 science papers that came out earlier this month.
And one of the things that was noted in those papers, and I saw from the NASA headline, and I've heard this term bandied about for Bennu, is that it's like a ball pit, right? You guys took your tag arm and you shoved it at Bennu, and we were all calling it a gentle boop before it happened. It did not turn out to be such a gentle boop. It actually went into the surface by about half a meter.
Yeah. And it was fairly unexpected. I mean, we had done simulations of a number of different materials. We sort of had, we had almost like a catalog of potential results that we were considering. But this was a bit more unexpected than I think we had originally conceived. And so, between this and one of the experiments that was conducted by the Hayabusa 2 mission called the Small Carry-On Impactor Experiment, where they basically shot a little ball bearing into the surface of asteroid Ryugu, we're beginning to put together this picture that really carbonaceous asteroids like Bennu and Ryugu they have very weak surfaces. And I think it's still unclear whether or not those properties will be the same on asteroids that are not carbonaceous but stony asteroids that are composed of more more rock forming minerals, things that we expect to see on asteroid Apophis. And so one of the cool aspects of doing OSIRIS REx with our spacecraft and sending it now to Apophis and turning it into the OSIRIS-APEX mission is that we're going to be able to perform some pretty similar experiments on Apophis as we did on Bennu, and maybe tease apart whether or not these objects, these two different rubble pile asteroids, have the same type of surface properties, or whether they're distinct because they have distinct compositions.
All right, well, I want to talk to you more about OSIRIS-APEX, but first I want to welcome people from where they're watching. Welcome from the Antarctic Research Station, Fort Lauderdale, Columbia, Cottondale, Florida, the UK, Scotland, Buenos Aires, Ohio, Ontario, Canada, Tallahassee, Serbia, Norway. Wow, just all over the world today.
That's awesome.
Greetings to Ron on the bayou in Louisiana. Always watching. Thank you so much, Ron. Let's see if there's more. Scotland and Leonora, Washington. So, wow. And also, thank you to Moon for the super sticker over on YouTube. Much appreciated. So really, thank you so much from the bottom of our hearts. We are a 501c3 nonprofit. So if you like these kinds of outreach programs that we do, feel free to drop bits over on Twitch, stars over on Facebook, super stickers, super chats over on YouTube. We appreciate all of those. So thank you so much. All right. Okay. OSIRIS-APEX. So this is where you're going next. We're going to talk about Bennu, I'm sure, a lot over the next few years, but I want to find out what the plan is with this particular mission. You're not going to be able to take a sample. That's been done. That arm doesn't do anything. There's no case there anymore. So what are the plans? What sort of science are you hoping to do at Apophis?
Yeah, so I'm so excited about the next phase of the mission, visiting asteroid Apophis. So I guess just to set the stage for when we will be encountering Apophis, Apophis makes this exceptionally close approach to the Earth, April 13th, 2029. And we know when it makes that close approach, it's going to be 1/10 of the distance between the Earth and the Moon. So it's actually going to be a little bit below the distance of most geosynchronous satellites, which is crazy. We will be able to see it with the naked eye during close approach in parts of Europe and Africa. And I think that's probably the first time in human history we'll be able to see an asteroid this bright, this closely. So it's going to be, I think, a crazy event from just like a media perspective. You know, people will really connect with the fact that these asteroids, they can get super close to Earth. And I think that's a good thing. So we start observing Apophis about 2 weeks before its close approach. And it'll just be a point of light at that time, but we'll be able to see how its light gets a little brighter and a little dimmer as it's rotating. So we're going to be able to watch how its rotation rate, or the length of a day on Apophis, evolves as it goes in and out of Earth's gravitational well. When it is at its closest approach, we have a lot of indications that it is going to get tidally torqued. We know that its orbit will change. So its semi-major axis, or the distance from the Earth, or from its distance from the sun, is going to increase. Its closest distance to the sun is going to increase, and its orbit is going to get larger as a result of this. Its rotation rate, the length of a day, will probably also change, and that's why we want to watch it throughout that whole process. And maybe its surface is going to get modified as well. So we're unlike Bennu, which, we approached Bennu, we did a lot of careful studying, and then we grabbed a sample. We're going to be examining Apophis right after it undergoes this exceptionally rare planetary tidal encounter with a major planet. These type of events only happen about once every 7,500 years with the Earth. So wow, pretty unusual on a human, on the scale of human civilization, right? And that's just the beginning. That's just the first couple months of the mission. So after that, we'll go into close orbit around Apophis. We're going to study it in detail like we did at Bennu. And we're going to try and really characterize any surface motion or any changes that might have been induced by the tidal event, as well as just characterizing it, because Apophis is an asteroid that gets really close to our own planet. It's considered a potentially hazardous asteroid, and it's a good analog for other potentially hazardous asteroids. So we want to characterize it as a representative object of what might eventually be something that might eventually be on a collision course with our own planet. But last but not least, we also want to do an experiment similar to the sampling or the tag, we called it touch and go or tag maneuver on Bennu at Apophis. So as you pointed out earlier, our sampling arm will no longer work, but we will be able to get very up close to the asteroid with our spacecraft thrusters and move some material around. We did that at Bennu, not on purpose. We did that just because we got so close when we were sampling. It was inevitable when we did our back away burn with the spacecraft. And we learned a lot from that because the thrusters can exert a known force. And so seeing how the surface responds to that interaction with the spacecraft thrusters gave us a ton of information. And we plan to do the exact same experiment at Apophis and really get at, okay, how strong, how cohesive is the surface of this rubble pile asteroid? Is it really weak like Bennu, or is it maybe a little more cohesive because its composition and the minerals that dominate its surface are distinct? And that will have incredible science value, but it will also teach us some things about how we might mitigate a potentially hazardous asteroid like Apophis in the future, should we ever need to do something like send a kinetic impactor to it.
So when we compare Bennu and Apophis, how different, what are some similarities, what are some differences that we're already aware of between these two asteroids?
It's a great question. So they're fairly similar in their size. They're both about Apophis is a little smaller than Bennu, but they're both about as wide in their greatest dimension as the Empire State Building is tall. And so we know that, they'll probably have similar masses. And that's good to know because we understand that we have a good understanding of how our spacecraft was able to go into orbit around Bennu, which is a really small object. We actually won, I think, a Guinness Book of World Records accolade because we went in orbit around the smallest solar system body, and we hope to break that by going into orbit around Apophis, which is just a little smaller. And we think Apophis is also a rubble pile like Bennu was, but the overall composition, the types of rocks that dominate Apophis are quite different from what composed Bennu. So Bennu, as I mentioned earlier, is dominated by hydrated minerals or water-bearing minerals. These are things like clays. And we also saw some organics or some carbon-bearing molecules on Bennu. We don't think there's going to be those types of materials on Apophis. We might be surprised. There might be small amounts, just like we were surprised at Bennu finding pieces that look like Vesta on its surface. But in general, Apophis is going to be composed of more what we think of as traditionally rock-bearing minerals, things that form at higher temperatures, and they're stronger and a little more competent. And Apophis's rotation rate is also much, much slower than Bennu's, and it's in all likelihood going to change as part of that close encounter with Earth. And so we'll have a little bit more what we would call operational complexity. So we're going to just have to think on our feet a little more quickly and maybe replan at Apophis, because it's likely that what we know about it now is going to change shortly after we get close to it in the 2029 timeframe.
All right, we're kind of winding down towards the end of our show. We've only got about 10 minutes left, and I want to make sure we get some audience questions. So feel free to ask your questions in the comments, in the chat, whichever you're watching from. And I do have one, and I wanted to ask it anyway, so I'm going to go ahead and ask it from our viewer, Moon. What is meant when you say a signature of organic material in the composition? What are we talking about?
Yeah, so it's a great question. So what we are basically seeing is something that a carbon-bearing molecule that has a specific structure. And so we think that, and we see in meteorites that look really similar to Bennu, sometimes we see this sort of, it's like a carbon-bearing material, but it's what we would call amorphous. It's glassy. It doesn't have a specific well-defined structure. But when we looked at Bennu in the visible and really the near infrared wavelengths, we did see some glimpses of spectral signatures that indicate carbon in specific ring structures. And so this gave us confidence that those features are due to organic molecules. And it's really important when we identify these things to try and get a grasp on what they are, because these are things that could have been precursors to life on our own planet. But the best way we are going to get a handle on what exactly is present on Bennu is by studying the sample. We can examine what those molecules are with much greater precision and accuracy. And so right now we have some glimpses, but the sample that's getting returned next year is going to be more definitive in terms of what type of organic compounds exist on Bennu's surface. And it's really exciting. It's also one reason why we've had to keep everything very clean and pristine on the spacecraft, so that we, when we look at that sample, a year and a half from now, we know that everything that we're finding is from Bennu and not from some sort of contamination source.
All right. This next question is from Charlie Doyle. Why did you want to sample from a recently excavated crater on Bennu?
That is a great question. So when we looked at the surface of Bennu, we did see a lot of indications that the uppermost layer of the asteroid's surface had been altered by the space environment. And so this includes, bombardment by tiny meteorites, what we call micrometeorites, as well as by the solar wind. And what our working theory is that these processes they change the composition ever so slightly of the nearest surface, and we have a good indication of this because most of the asteroid is a bluish color, but recently excavated small craters actually look red. So we know there's some difference, and we also those sort of processes, exposure to the solar wind and solar radiation, as well as micrometeorite bombardment, likely will also break down organic material. And so if we want to sample the organic material present on Bennu, going to an area that was recently excavated is probably our best bet. And we'll get the sample soon, and we'll be able to confirm whether or not that hypothesis is correct.
All right. I want to give a couple more shout outs here. Greetings to people watching us from Woodland, Texas, and Mount Vernon, Washington. I know where that is. I have a friend who actually goes there. And also a big shout out to Freddie on Facebook for sending us stars. So thank you so much, Freddie. Once again, we are a 501c3 nonprofit, and these programs happen because of your support. So if you want to continue supporting us, if you want to throw us a few bits, some stars or some YouTube super chats, we appreciate it. And also you can always donate at our SETI.org/give now. If you want to do a little bit more than just throw a few stars and bits and super chats at us. We appreciate all of it. I've got one more question from an audience member. It's an interesting one. This is from Sunny in North Fort Myers, Florida. For dangerous obstacles, would we send a drone with a railgun to mine the asteroid and expel the slag in the direction of the desired position? Which is preferable? How do you think we should handle some of these potentially hazardous asteroids if we need to move them?
It's a really good question, and there's a lot of good ideas that are out there. I think we need more data to really answer this question, and fortunately, we are going to be getting that data, at least for one of these mitigation techniques, which is called the kinetic impactor, around the same time we're returning the sample of Bennu next year. So next, I believe it is also next September, towards the end of September, the DART mission, which is this planetary defense kinetic impactor demonstration test, is going to be slamming a spacecraft into one of the asteroids in the binary Didymos system. And then we will be able to examine the after effects with 2 CubeSats that are being provided by the Italian space agency, Laika and Leia. Laika Cube, Luke and Leia. Two CubeSats named Luke and Leia. I love it. And so, you know, the kinetic impactor as a planetary defense mitigation strategy, I think is one of the best ideas that we have. And we're going to get hard data on how effective it is next year, which is really exciting. But there's a number of other ideas in the mix. There's, of course, some nuclear options. There's things like a gravity tractor where you just sort of park a spacecraft in close proximity to an asteroid and then let that, you know, slowly, that gravitational influence slowly change its course over a long period of time. But we need more empirical information, I think, to ultimately identify what is the best technique for mitigating a future threat to our own planet. And so I'm really happy to see NASA's planetary defense arm kind of get a little stronger and start testing out some of these ideas. And I'm really excited to see what DART does next year.
I'm looking forward to that one too. That's another really good one, and hopefully we'll have someone from DART on this, you know, here on SETI Live when we have some information to share with everybody. Once again, this has been SETI Live, and I've been speaking with Daniella Dellagiustina from the University of Arizona, and we've been talking about the extension of the OSIRIS REx mission to go visit asteroid Apophis and become the OSIRIS-APEX mission. So thank you, Danny, for joining us today.
Yeah, my pleasure. Thanks, Beth.
Absolutely. And everybody, once again, you can check out our website at SETI.org. You can sign up for our e-news there. You can make a donation to any of our projects that are listed or just a general one and help us out, keep us running. And also, we will be having next week, we'll be talking with someone from the InSight mission, which is unfortunately ending this year. But we're going to talk about what the end of that mission means and what science we've gotten from it and what science we expect to get over the next few months that are left. And stay tuned for another SETI Talks event coming up next month. We just had one yesterday. The video is now live. So if you go to our YouTube channel, you can check out that new video. We talked about JWST and how it can be used, what we're expecting from it, what we hope from it, and how it might even be used for looking at exoplanets and planets in our solar system. So go check all of that stuff out. And once again, everybody, thank you so much for tuning in from wherever you are watching, and we'll see you next week.